go through some mathematical notations, although it should be high level, but I will go through them with you to make sure that you understand these fairness definitions. So first of all, this is for binary classification. So we have applicant, we have the application for that applicant, we have this machine learning system, and then we have the outcome. Applicants in the application, we could have sensitive attributes, like, for example, gender. And I'm going through the examples with gender. But these sensitive attributes could be, for example, race, age, etc. And a couple of non-sensitive attributes. And we could have an outcome of the system, which is y, yes. And then the decision, which is predicted from the system. Right? So in the classification, we always, for the supervised, we have labels. So labels is actual outcome y, and D is the predicted from the system. Is it clear until now? Okay. So the first definition, which is very well-known definition, is statistical parity. It's called also demographic parity, group fairness, equal acceptance rate, benchmarking. What does it mean is that the probability of getting the decision for the population of female should be the same as probability getting the positive decision for the population of male. So it should be equal probability of getting a decision for both populations. The problem here is that in demographic parity, there is no way of saying that, for example, these people should be qualified. Right? It's just saying that the population of male and female should be the same. It's not saying that if they are getting a loan, it should be qualified to getting the loan, right? So it's not really fair in that sense. So they also propose another version of demographic parity called conditional demographic parity. So they add this legalized factor. So for example, if you are applying for the credit card, legalized factor is credit score. So at least you have a good credit score in order to get credit card. And then the population of male and female should be the same. But there is also another problem with demographic parity, is that in the ideal world, that we know actually who should get the loan and who should not get the loan, and this is fair, and we are God. Demographic parity is not fair. So it's saying that the system is not fair, because its probability is not actually happening. So if the population is different, demographic parity cannot actually do anything about it. So it actually says it's unfair in the ideal case. So that's why we have also other definitions of fairness. Two of the most well-known group fairness definitions are proposed by Marit Hart, which called equal opportunity and equalized odds. Equal opportunity or false negative error rate balance is considering the predicted outcome. So it's mostly for the classification technique. So we have the true outcome and the predicted outcome from the system. And say that the true outcome for the negative and positive should be the same for the both population. What does it mean is that we should come up with a threshold. For each population, and saying that, for example, this is a threshold for female population to get the positive outcome, and this is a threshold for the male population to get the positive outcome. There is another group fairness measure by Marit Hart called equals odds. So equals opportunity is talking about the positive outcome. Equals odds is also positive and negative outcome. So instead of having one threshold for each population, we have to have two thresholds for both the positive case and negative case to pick who should get the positive outcome or not. Is it clear until now? Okay. So these are the most well-known group fairness measures I wanted to present here, but there are other fairness measures that you can actually check. But what is individual fairness? There are three also measures for individual level. One of them, these are actually talk about it a lot, is the fairness through unawareness or blindness. If we don't see the gender, we cannot be unfair towards them. So if we are not actually in the data having like the column of gender, we are not going to be unfair. But that's not true. The thing is that you already learned throughout the summer school that the deep learning, at least, are very good to learn representations. So there are so many attributes that you can actually predict this from those attributes. For example, that person is female or male. So fairness through blindness is not necessarily fair because we can do it. Also because of this indirect discrimination. So for example, if we have a person going to the wealthy university, because it's a female university, if we have it in the data, we are pretty sure that that person is a female because of this correlation. So there is another definition which is called causal discrimination. Causal discrimination is saying that we can keep the sensitive attributes, but we have to make sure the outcome of the system is not depends on the sensitive attribute. What does it mean is that if we keep all the non-sensitive attributes the same and only change the sensitive attribute, the outcome of the system should be the same. And this is one of the practical way of resolving the issue of individual fairness, because the main definition, which is coming from this work by Cynthia Dork, is saying that if we want to satisfy individual fairness, we have to define two similarity metrics. One similarity metric saying that these two individuals are the same, and another similarity metric saying that the outcome of the system is also same for them. It's really difficult to do. It's very nice in theory. It's very difficult to do it in practice. Why? Because we cannot really define a similarity metric for individuals. In binary classification, we always have this decision line that we have to draw and say that this is a positive instance, this is a negative instance. And the instances, if they're close to each other, we need to draw this line anyhow. So how we can make sure that this similarity is this similarity that we are proposing is enough to say that although these two are similar, we are actually not giving them the same property. So it's very, very hard to satisfy in practice. So there is no paper actually working on this definition at the moment. There are some approximation of it that they are doing. But that's all.